Hey, welcome back to Math with Patrick. Today is December 26th, and we're solving problem 360 from the Daily Epsilon calendar. The answer today, x, should be 26 because that matches today's date. All right, we have a geometry problem. We have a square here. We have a diagonal from the top left of this square to the bottom right of whatever this segment is. And we're being told that these lengths are all the same. So these four should all be the same. But then also, this little diagonal on the outside of our square, reaching down to the bottom right corner, is the same length. I think for ease of writing this whole expression throughout my problem, I'm just going to call this A. And then towards the end, I'll hope to find some kind of expression like x equals, and then something in terms of A. Hopefully then we can show that x is 26. So the first thing I'm noticing is that we have some similar triangles. We have a smaller triangle here whose hypotenuse is A and longer leg is x. And I think we could get an expression for this height here in two different ways. One way is that we do have this line right here. We could try to write an equation using the slope of this line, and we could get an expression there. We could also just use the Pythagorean theorem, and I think that's a bit easier. So I'll just do that right now. When we have the missing leg, we're going to do the square of the hypotenuse and then subtract the square of the other leg. And then now looking at our larger triangle, we have a base of a plus x, and then we have a hypotenuse of, all right, well, that's going to be a little bit tricky to figure out. Maybe instead, let's just label the shorter leg. That's just going to be A, and that's a little bit easier to deal with. So I think then we can set up a proportion with our similar triangles. Let's set up two fractions, set them equal to each other, and then I'll do the short sides and then or the short legs and then the long legs. So on the left side, I'll have both lengths of the short leg, starting with the left triangle and the right triangle. And then in my right fraction, I'll do the same thing, but with the longer legs. So I'll do x and then a plus x. And usually at this point, when you have a proportion, you can just cross multiply your fractions. The idea is that we're multiplying the left side by the right side's denominator on both the top and bottom. And then we're multiplying the right side by the left side's denominator on the top and bottom. So multiplying by the number 1 here and the number 1 here won't change the value of either of my fractions. And then what's convenient is that in the end, we do have the same denominator on both sides, and we can end up dropping them. So in short, usually you'll just see folks circle it like this, but there's a larger explanation if you really, really want it. We get a plus x times the square root of a squared minus x squared. And then on the right side, we just have x times a. And of course, we could put this denominator on both sides, but I'd rather not because that just seems to clutter up my work. Maybe we could try to simplify or get rid of the square root by squaring both sides. So let's just try that out and see what happens. And then we'll get a squared minus x squared, and then a plus x. Oh, and kind of interesting, this is a difference of squares. Oh, sorry, I forgot to square this side as well, or this particular factor. This difference of squares can be factored as a plus x and then times a minus x. So why not? Let's actually tack on another a plus x in this term, and then we'll just call this one a minus x. All right. I don't really see where we're headed, just we don't have square roots anymore, which is kind of nice. Maybe we could try to get this thing looking like a polynomial in standard form. That would require me to expand the left side. Good thing I know the binomial theorem. That makes this easy. This will be a cubed plus 3a squared x plus 3ax squared plus x cubed. And then we're still multiplying all of that by a minus x. And then on the right side, I'll just keep it the same. Then I guess I could distribute everything. So all of these terms get another a in them. And so I'll just raise all these exponents by 1. And then all of them will also get another x, and then all of them will turn negative. Maybe I'll try to line up my terms as well, because I'll get this minus x times a cubed, and that should land somewhere here-ish. So I'll go minus x a cubed. We'll get minus x and attach it to this one. So we'll have minus 3a squared x squared. So minus 3a squared x squared. Kind of cool that those will cancel. We'll get minus 3ax cubed. So I'll put that here, minus 3ax cubed. And then finally, we'll get minus x to the fourth. I'll just put it somewhere else. And then still on the right side, I'll keep it the same. Maybe I will write my polynomial in descending order of x, because that's just kind of typical. We're also solving for x, so might as well get the attention on x itself. Let me cancel these out before I do anything. And then, okay, so I'll move my negative x to the fourth to the front. Then these two together will combine to a negative 2ax cubed. Use those up. This one canceled. Although maybe I could subtract this x squared a squared over to this side. And I'm going to do that anyway if my goal is to get this polynomial in standard form. This together would create a plus 2a cubed x. And then finally we get a plus a to the fourth at the end. Okay, so it's starting to look more like a standard form polynomial. I mean, it kind of is, but I do prefer it when my leading coefficient is positive. So I could flip all of those around. And all right, I think at this point, I want to divide everything by a to the fourth. The idea here is I don't like this kind of double variable stuff going on. And I think by dividing by a to the fourth, I will get something a little bit better. And then I am technically dividing both sides by a to the power of 4, but fortunately, 0 divided by some kind of positive number will still be 0. This creates x over a to the power of 4 plus 2. And then if I think about this a to the fourth down here, it's only going to cancel with the a's. I'll get 3 a's on the bottom. I have 3 x's on the top. So I think I'll write this as x over a cubed. And here's my idea. I'm getting this polynomial in terms of x over a, and we could just substitute that out for some kind of variable. We could call it y or something. But this is looking a little bit more like a polynomial to me. We'll get plus x over a squared minus 2 x over a, and then finally minus 1 equals 0. And this is a quartic polynomial. Let's try to rewrite it with maybe that substitution here. Y is equal to x over a, y to the fourth plus 2y cubed plus y squared minus 2y minus 1 equals 0. What's like kind of neat is like this chunk right here we could factor, but I don't see how this is too helpful just because we are kind of abandoning the right side of this polynomial. Maybe there's a way to factor this as two quadratics. I guess if we were to factor it, we could try finding some rational numbers using that rational root theorem. Seeing that these are both 1, the leading coefficient and the final coefficient, I do know that if we have rational roots, it's basically just going to be plus or minus 1. So we could try plugging that in and see what happens. If we plug in a positive 1, we get 1 plus 2 plus 1 minus 2 minus 1. So that doesn't give us a 0, so that shows me that positive 1 is not a root. And then if we try with the negative 1, we'll get 1 minus 2 plus 1 plus 2 and then minus 1. These would cancel, and I still get 1 equals 0, which just isn't true. So thinking through the rational root theorem and realizing that neither of our rational roots work, this is probably just going to be a little bit of a gross answer for the roots. I'm just going to use Wolfram alpha to port over the potential solutions for this one. So here's the polynomial. Looks like we have 2 real roots. And then given that it is a quartic polynomial, we have 2 imaginary or complex roots. Here are those real solutions and complex solutions. Given that it's a geometry problem, we're only going to be working in real numbers, so I can ignore the complex solutions. And these are the same except for this plus or minus sign. And so I'm assuming that this top one is going to be for the negative value here, just because if we're subtracting a positive number, this one will be less in value than this one. So I'm going to grab this value right here for y back on the whiteboard. Also, Quill just joined us, so he's here for this algebra portion. Here's our value for y. Y is the same thing as x over a, and the whole point here is that we're solving for x. So let's try to isolate it. I guess all we really need to do is multiply the a to the other side. And then I guess we should also substitute in the value for a. So a is going to be 13. Maybe I'll combine the 13 over 2 together, and then I'll keep the square root stuff on its own. Just because I feel like I'm going to need to expand this product on the right side, and the 13 and the 2 can live alone for a sec. And when I deal with all this stuff, I could do the 13 over 2 after all that. So we now get some kind of gross looking product with all of these square roots. Hopefully out of all of this, we get the number 4, because 13 halves times 4 does give us 26 for today. So maybe that's what I'll do. I'll just try to expand all of this, and let's see if we get the number 4. I am going to treat it as a binomial times another binomial. I'll just shove these two together as one thing. So we get the first times the first. So there's that first term, and then here is the second. So these two. And then I'll do the outside terms plus, and then since they're both under square roots, I think I'll combine them. So I'll combine them like this. 5 plus 4 root 2 times 2 root 2 minus 1. Then we do the inside terms. This negative sign will just flip the signs on that guy. So it's plus 1 minus root 2. And then this minus 1 and that will just create a minus root 2 root 2 minus 1. Somehow this is all just the number 4. I guess it could be useful to expand as much as I can and try to find cancellations. So this minus 1 and that really don't do much. It's just minus and then 5 plus 4 root 2. And after multiplying in the negative 1, I'll also multiply in this root 2. So I'll get the square root of, and then 2 times 5 plus 4 root 2. So I get 10 and then 8. So maybe let me put this here, plus root, then 10 plus 8 root 2. Okay. For the next one, I wasn't really excited to do this one just because there's so much multiplication going on. First times the first is 10 root 2. Outside terms give a minus 5. Inside terms is 8 times 2 is 16. Last is minus 4 root 2. So it's, I guess, kind of convenient that these kind of combine to an 11, and then these combine to a 6 root 2. And then I don't think there's really much else I can do to the bottom ones here, so I'll just keep them the same. Plus 1 minus root 2, then minus root 2 root 2 minus 1. Okay. Something that's actually a little hard to spot. I think this right here is a perfect square. We could split the 11 as a 9 and a 2, and then keep that 6 root 2 the same. And this would be the same thing as 3 plus root 2 all squared, right? Because this squared is 9, this squared is 2, and then twice the product of these gives us our middle term. So this square that we found cancels with this square root, and so we're just left with 3 plus root 2 in this spot. 3 plus root 2. This plus root 2 cancels with this minus root 2, and then weirdly, this 3 and this plus 1 combine to get our 4. And this is what we wanted, right? Because all of this nonsense needs to be the number 4 to multiply here and get 26. So that means that the remaining ones need to cancel out. We have one that's positive and two that are negative, so I could set up an equation here and set them equal to each other. This means that root 10 plus 8 root 2 must be the same as root 5 plus 4 root 2 plus root 2 root 2 minus 1. To prove that this is the case, maybe let's just square both sides. We'll get 10 plus 8 root 2 on the left. Squaring this, let's see, we'll get the square of the first term, which will just remove that square root sign. Square of the last term, which will also remove that square root sign. And then plus twice the product of both. Okay, so we have to multiply these together. But then, wait, didn't we already do that, though? That was this times that. Yeah, cool. And that gave us this one. And this was the term with that fun cancellation. This was the one that gave us an 11 plus 6 root 2. And we figured out that this was just 3 plus root 2. Wow, okay. So this interesting cancellation of the square and the square root shows up again. And this square root sign cancels with the square that we get here. And so we just get 2 times and then 3 plus root 2. So hopefully the left side and the right side are the same. Maybe let's expand this one down here. We get plus 6 and then plus 2 root 2. And then I can erase this part right here. Okay, moment of truth. This should be equal. If it is, x is 26. Here's a 10. Here's a 5. Here's a 6. Here's a minus 1. Cool. So we get 10 on the left, 10 on the right. Then we have 8 root 2, and nice. Okay, we have 4, 2, and then another 2. We have 8 root 2 on both sides. Everything cancels. These things are equal to each other. So in here, they all zero out. So we're only left with the number 4. And then finally, we can do 4 times 13 halves, and we get 26. Wow, what a crazy problem. I don't know if there's a better way to do it, but this is the way that I found. So thank you for watching. Hope you enjoyed, and I'll see you tomorrow.